Chapter 36, we're going to talk about star death. What happens to a star when it dies? We already kind of talked about star life. Stars start as a cloud, as a big cloud of gas that gets pulled in by gravity and starts spinning around and forms a disk with a star at the middle and a solar system forming around it. Do y'all remember that from last time? Yes.
On the quiz, I didn't understand the question. It was like, what does this chart measure?
Heck yeah.
And I said like something in size. And it
Nope.
was, like, how is it not size?
Because temperature on this axis, luminosity on this axis.
But isn't it also the luminosity, like it increases in size as it goes up?
It does. But what's on the axes, which is what the question was asking, is the relationship is between temperature and luminosity. So, this is the chart showing temperature going to the right, it's starting hot on the left, cold on the right, and luminosity brightness going up. And this is the main sequence. Stars start on kind of this side of the chart, and they get smaller and smaller as the big gas cloud falls inward and heats up, and then fusion starts at the center, and the star is burning, fusing hydrogen into helium, and then after all the hydrogen gets used up, it fuses helium into carbon, and then the star starts to die. Because most stars, if they're small, they can't fuse the carbon that starts to form at the center. And so they start to die and they go up this way. And that's what we're going to talk about today, the death of a star. So we're talking about a death of a low mass star. So everything you see from here to about there, we consider that a low mass star. Everything from here up on the main sequence, we consider to be a high mass star, a very heavy star, and they die a lot differently than a low mass star does.
Is there a way where you can judge whether or not it's a low or high mass star, or do you just eyeball it?
Yeah, there's different ways. One way is because stars often exist as binaries. Over half the stars are binaries, a star with another star next to it. And they orbit one another, and you can tell by how fast they're orbiting and by how hard they're pulling on one another if it's heavy or light. That's kind of the most common way to weigh the star. There's other ways, though. You can see if the star is of a certain, let's say that a star is of a certain temperature. You know it's a blue star. It's very likely to be a big star, a heavy star. Because almost all the blue stars are. You see what I'm saying? Mm-hmm. And the reason why a blue star is heavy, it's because it's got a lot of gravity, and it's really pulling its gases in, so it's fusing them very quickly. And that creates a lot of heat, which makes it hot, and makes it blue. So there's different ways to tell that a star is heavy. One by its color, another by how it orbits. There's some other ways too. We don't want to get too far into that. It just kind of gets boring. So we're going to talk about these stars right here, low mass stars, when they die. And what happens when they die? So they start out mostly hydrogen. We need a little more light, I think. Not a lot, but a little. You know how I get a little more light?
How?
I pull this cord. That cord means little more light. That was on the cord instructions. There we go. Is that better?
Worse.
Yeah.
Okay. So
It's Jack Burns.
I need another eraser. Let me erase this. Bam.
So we're one of the few stars that's not binary.
Yeah, well, when I say few, about 51% of the stars are binaries. We're in the 49% that's not. We're slightly out of the norm.
Are there any more than 2? No.
Yeah, there are. There are 3-star systems and 4-star systems that kind of all go around one another in a little dance of stars. But and there's more than that, but that's pretty rare. That's like 1% or less of the systems are 3 or 4 systems.
Could it be because they're revolving around each other and they're pulling each other? Would one star fall into another?
It could eventually. Stars can spiral into one another and hit. And we'll talk about some star collisions in a couple of chapters.
Oh my gosh.
Yeah, that can often cause a huge explosion. Especially a collision between 2 neutron stars, which we're going to talk about that. When you get 2 neutron stars collide, you get a black hole forms. We're going to talk about that later. So we got a lot of good stuff to go here. But so in our sun, here's what's happened. In the last 5 billion years, before we were born, hydrogen has been converted into helium. And so the star started out probably at about 90% hydrogen. And now it's down to about, is it 75%? Is that what we read? 75% hydrogen now, and 25% helium. And this number is just going to keep going down, and the helium's going to keep going up in the center of the star. And pretty soon you're going to run out of hydrogen. And all it'll be left with is helium. And when that happens, gravity really pulls in, because there's 2 forces you have to understand at work here. There's the force of fusion causing energy and pushing the star out. And then there's the force of gravity pulling the star in. And if the fusion stops, then gravity takes over and really pulls the star in hard. So when hydrogen fusion stops, the gravity will take over, really pull hard in on the star, and that'll be enough to fuse the helium. Santana, you with me? The helium in the middle starts changing to carbon. And the percentage of carbon starts to go up. This is really cool. The middle of the star will start to form a ball of carbon. And so what it'll look like is carbon on the middle, surrounded by helium, with a little hydrogen on the outside. The sun starts to form layers like an onion. Now you know what this big ball of carbon in the middle of the star is? It's a giant diamond. The center of our sun is going to be a giant diamond, which can get up to the size of the Earth in some cases.
Is there any coal in there? Because
if you compress coal enough, you get diamond. And there's so much gravity in the middle of a star, you skip the whole coal portion, and you go straight to diamond.
Wait, what?
Did you know a diamond is just pure carbon that's been compressed in the Earth? So carbon will start forming from helium fusion in the center of our sun. And you'll have a big diamond in the middle of the sun. It's going to be important in a minute. But what happens at this point is when helium starts fusing into carbon, you get a lot of energy from that process, and it pushes the star outward. And the star will get bigger. The hydrogen that's on the outside gets pushed outward, and the star just literally starts growing in size. Once we get to this phase where helium starts fusing into carbon. And the sun will go from this size to this size. And the sun, as it's growing, will get larger and larger and larger. It'll swallow up Mercury. It'll swallow up Venus. We think it might swallow up us.
You said it'll go up from that little dot right there?
From that size of that little dot all the way to the size of this. This is called a red giant. All the red giants that we see out there are dying stars like our sun. This process takes about 100 million years to go from here to here.
How much longer do you think we have?
We have 5 billion years before this process even starts.
We're good.
We got about 5 billion years
Enjoy it
to
every
figure
second.
it out.
YOLO.
And then the sun will start expanding and it's going to swallow us up probably, or get so close to us that it burns us up. But we may be able to move the Earth away from the sun at that point. How do you move the Earth? I've read about it. What you do is you take a big asteroid and you nudge the asteroid so that it comes near the Earth. This is a great plan that science fiction writers have for moving the Earth. And so if, let me get some magnets here. Oh, here we go. This is perfect. So if this is the sun, I'm kind of getting off topic. This isn't even in the chapter, but it's fun to talk about. Here's the sun. Here's the Earth orbiting it. And if we need to move the Earth, what we do is we get an asteroid that's pretty big, and we knock it onto a course where it's orbiting the sun and the Earth. And every time it goes around, it pulls the Earth a little bit. Pulls the Earth a little bit out. See what I'm saying? Pulls the Earth a little bit out. And they calculate that they could nudge an asteroid that's big enough size onto this path, where every time around, where it goes around about once per year, and it pulls the Earth about an inch.
How do you nudge?
That's all you need.
How do you nudge an asteroid?
You nudge an asteroid by flying a spaceship at it that has a little solar reflector, kind of like a parabolic dish. When I say little, I actually mean big. It has a big parabolic dish and can shine sunlight on it and focus the sunlight onto the surface of the asteroid and burn the asteroid a little bit where it shoots off gas or ice. We could do it with a comet too. And if you heat up one side of it and that shoots off gas or ice, it'll shoot it in a certain direction. It'll nudge it the other direction.
So everything has to go completely it has to go perfect.
Yeah, and then you get this thing on the right course, and it pulls the Earth about 1 inch a year, and that's about the rate that the sun was going to expand.
So every year.
So every year we just move a little farther as the sun expands, and so for 100 million years we'll be getting farther and farther away.
Until we run into
Simple as that. You just move the Earth.
So every year.
Is that what makes that asteroid stay in that orbit around the Earth?
Because it's moving. It's the same thing that makes the Earth stay in orbit. The sun's gravity pulling, and the Earth trying to move away. And the combination of the two, a pull and moving away, gets an
There
orbit.
wouldn't be a point that the sun would just pull it like in front of the Earth. You know what I mean? Like
Not if you had it in the right orbit.
But what makes the asteroid be able to pull us away instead of us just getting pulled? Like, how we have to stay in that, how come the asteroid can make us go farther?
Because every time around, the asteroid pulls a little on the Earth.
So every year.
It's just the
we
way
see-
physics works.
Every year we see an asteroid crossing our atmosphere. Kind
No, it wouldn't get that close to us. It wouldn't be coming in our atmosphere, and then it would plunge into the Earth.
of.
Stays out in space.
In space, like.
Yeah, you'd see an asteroid go by in space. It would just look like a star from here. Easy plan. So we could potentially move the Earth. Of course, that's 5 billion years away. They might have a better way to do it now. Think of it. We went from horse and carriage to space shuttle in less than 100 years. What's it going to be like in 5 billion years?
Hoverboards.
Who knows?
I don't even have those.
Okay, so what's going to happen is the sun is going to expand and expand and expand, and eventually gets real big like this. We call this a red giant. And it's way bigger than the sun. It's actually brighter than the sun when seen from a distance because it's so big. But it's cooler than the sun because the outside it's so big now, there's the energy that's coming from the interior of the sun is now spread out over a much larger area, so it's cooler, and that's why it's red. It's bigger, it's brighter, and it's cooler. That's a red giant. You see several red giants in space right now, same thing's happening to them. Then what happens? Well, the star gets so big that its gases just fly away. The hydrogen on the outside, remember I said it was like layers? There's hydrogen on the outside, and helium, and carbon. The carbon center is actually much smaller. A little bit of carbon in the middle. And what happens is the star expands and expands, and the hydrogen floats away, and the helium floats away out into space and becomes part of space gas. Space gas. And you're left with the carbon core at the center. It's really hot because it was in the middle of the star. That carbon core is not doing fusion, by the way. Gravity is not strong enough to pull those carbon atoms together and make them fuse. So it's just a ball of carbon, a big diamond in space, Maggie. And that's what we see here.
Can you connect it?
There's the white dwarf, and we call that center ball of carbon a white dwarf. And so there's the white dwarf star in the middle, and there's all the gases coming away from this dead or whatever, dying star. And we call this object a planetary nebula. A planetary nebula is the remains of a dead star, with a white dwarf in the center that's glowing white because it's so hot. White or bluish white because it's so hot. And then all these are just the gases left from the dying star. And they're very beautiful.
Does it ever cool down?
It does. The white dwarf star will slowly cool down and will eventually get where you can't see it. We call a white dwarf star that cools down where you can't see it anymore a black dwarf. But it takes, scientists estimate, about 50 trillion years or so for a white dwarf star to cool down where it won't glow anymore. And the universe is not that old. The universe is only about, they think, 13 billion years old. 13.5 billion years old. We'll talk about how they know that. It has to do from the Big Bang theory. The universe started as a small point and expanded to the size it is. That's the Big Bang theory. But we can measure the rate that it's expanding and rewind to know how old the universe is. Well, if the universe is only 13 billion years old, and it takes trillions of years for a white dwarf to cool into a black dwarf, that means there's no black dwarfs.
Yeah, I was about to say.
It's a theoretical object that does not exist. Isn't that cool?
Looks like an eye.
It does. As a matter of fact, I think this one's called the Cat's Eye Nebula.
Nice observation.
Up.
Oh, wow.
Maybe that one might be the Cat's Eye Nebula.
That looks like
Not
a cat's
really.
eye.
That's the cat.
I think that's the Cat's Eye Nebula. Guess what that dot is at the center?
Sun.
The white dwarf.
That's the white dwarf. That's going to be what's left of our sun in 5 billion years. Our sun will be something like this. Cast off all of the
wait.
gases, and that will be what's
That's
left.
not the cat's eye. The previous one was the cat's eye. This one is the helix nebula.
Okay, that's the Cat's Eye,
Thank you.
and that's the helix.
Even though it looks like a legit eye.
Hey, they can call it whatever they want. If you discover one, you can name it.
That looks pretty.
Hey,
Yeah, these are beautiful pictures.
Hey, bro.
And what is this whole thing called? The whole thing.
Planetary nebula.
Planetary nebula. Why do they call it that? Well, the first person who saw one through his little telescope thought it was a planet. But he saw some gas too. So he thought it might be a nebula. So what's a good name for it? Planetary nebula. And that's what they called these things until they figured out what they were. Yes?
Is there anything in the universe that's like around like the temperature that we would have on the sun? I mean, not on the sun. I mean, on Earth. Like,
Yeah, a flame. a flame that glows yellow is the same temperature as the surface of the sun.
I'm talking about like, so like the temperature we have right now on Earth, like insane time, like 67 degrees or whatever.
Oh,
Is there anything that's even
like in space somewhere?
Yeah.
Okay, so this part right here is glowing, so it's hot. It's hot as a flame.
Mm-hmm.
This part is red, it's cooling. It's less hot than that part, right? So as you get further and further away, the temperature gets less and less. So there's a spot somewhere here that's that temperature, right?
Yeah.
Because deep space is really cold. So if this is really cold and that's really hot, there's somewhere in between that's just right. And that's where you find Goldilocks. Or the bears. I don't remember the story.
Goldilocks, yeah.
It's the Goldilocks zone. But of course there's no air or anything there, so you couldn't just like stand there and breathe it. But if you were in a spacesuit there, you wouldn't have to heat the spacesuit or cool the spacesuit. You would be the right
It's
temperature.
just because we've always talked about the extreme temperature.
Yeah, there are a lot of extremes. Yeah. We live at a tiny range of temperature where we find it
So
comfortable.
like out of all the stars that they discovered so far, like they haven't found any planets yet around them.
Yes, they have. Exoplanets. And you missed that. We talked about that before you came here. But a lot of the stars they find out there have planets going around them. They can't see the planets, they're too far away and the star's too bright, but they can measure the wobble of the star and know that there's planets orbiting around the star, pulling on the star. The stars are wobbling, and they can even measure the size of the planets that way. Also, when a planet goes in front of a star, it blocks out some of the light, and you can see the star dim a little bit as the planets go in front of it.
But it'd still be too small to see.
The planets are still too small to see. Coming up with some telescopes that might be able to image these planets. Giant telescopes that are interferometers, which you also missed before you came. Many telescopes working together, pointing at the same place in space, can see a better picture than just one telescope. So that before you all die, or actually, it'll probably happen in the next 10 years, maybe before I die, we'll be able to see another planet around a star that's not our sun. And that'll be cool. That'll be something that happens in the next 10 years or so.
Mr. Willis?
Yes?
All these things that we've talked about that you said are like, hopefully going to be happening in the near future.
Uh-huh.
How are they going to be happening without like NASA funding and everything?
They're not going to be happening without NASA funding. We have to fund NASA.
Isn't it like not being funded right?
No, it's being funded. It's just less. It's less than most people would like. But it all depends on the new president. Now, Trump, he's not that into science, so we probably won't have much NASA funding through his candidacy. But we'll see. You never know. Maybe he changes his
I
mind.
want to see a planet over there. We have seen white dwarfs. That's a white dwarf star right there around Sirius. Remember we talked about Sirius yesterday? Are you serious? Sirius is a real bright star that's kind of near us. And there's a white dwarf around Sirius. Sirius is a binary. That's called Sirius A, and that's called Sirius B.
So
Are you Sirius B?
Why isn't it bright if it's a star?
It's because white dwarfs don't glow. They aren't doing fusion.
Oh.
And that's real bright. That's doing fusion, and that's the white dwarf. It's not glowing very much, but you can still see it.
Well, Sirius ever lose
Glowing a little bit. What's that?
Sirius ever lose its fusion, like the brightness?
Yeah, Sirius will the same thing will happen to Sirius. It'll expand and become a red giant, and then there'll be two white dwarfs sitting next to one another, orbiting one another in space. Sirius was a binary. And for the longest time, there were two regular-sized stars next to one another. You want to see video footage on white dwarfs?
Yes.
Heck yeah.
Hi.
Heck yeah.
Hey folks, Phil Blake here. In the last episode of Crash Course Astronomy, I talked about the eventual fate of the Sun and other low-mass stars. Like, after a series of expansions and contractions, they blow off their outer layers, become white dwarfs, and...
That's way too long. It's 11 minutes.
Yeah,
You can watch it at home if you want to. I'll do the reading.
oh, that's cool.
Okay, this is cool. So when a white dwarf has a companion star, so
here's a companion. There's a white dwarf, Sirius B, and there's a companion star. Now, in some cases, the white dwarf is real close to the companion star. And then you get this happening. The white dwarf pulls material off of the companion star, and that material gets pulled onto the white dwarf, and then lands on it and causes a big explosion. And that's called a nova. Have you ever heard of a nova?
Yes.
And sometimes novas will happen over and over. Now, it's not a supernova. A supernova is a bigger explosion. But this is a small explosion called a nova.
It looks like it has rings.
Yeah, it does. The material gets pulled off, it circles around the white dwarf in a ring, and then it eventually falls in and hits it and explodes. So watch this nova video.
It's like an implosion, kind of.
Watch it. Pulling off of its companion. And get ready.
Boom.
Boom!
Wow.
That's a nova.
Oh my god.
And we see these big explosions in space. It just looks like a flash of light. And it occurs, they sped this up real fast, but it occurs time and time again as the stuff falls off of it.
Should we watch that again?
We call that a recurrent nova. You want to watch it again?
Yeah.
Space is crazy.
Stuff gets pulled in. Now, these two stars have to be close. The white dwarf has to be real close to this other star for it to happen. Boom!
Did that do anything to the star though?
No, just pull stuff off of it. It's not a big enough explosion to destroy the star. And see how it's just blinking? That's what we see. We see some stars blinking.
Is that one a twinkling star?
That's not what a twinkling star is, because you get a blink every 3 years or so. A single blink, a single flash.
Isn't the twinkling like...
Twinkling is caused by our atmosphere.
Yeah.
Our atmosphere is shaking.
Twinkling. I'm not understanding
Shaking,
what
shaking, little atmosphere.
Now there is a case.
I'm trying to think of that song.
There is a case where so much material can can get pulled off. It all depends on how close these two are together. If this one's really close, it can pull a whole lot of material off and get a bigger explosion, and the novas can be more frequent. They might happen up to once every 3 weeks or so. You get a flash, and so that's what a nova is.
So does that decrease the life expectancy of the star by taking material off of it?
Yes, this star wouldn't live as long because it's got material pulled
Wait,
off.
so how is the
Thank you.
biggest star getting stuff pulled off of it and the white dwarf is pulling that? I don't get that.
Okay, so each star has gravity.
Mm-hmm.
And just like we fall to the earth, things fall to a star because it has gravity. So if this white dwarf is close enough to this star, the gravity from this pull gas from the edge of this star. Especially if this star is starting to expand.
Mm-hmm.
See, if this star is dying on the left, it'll get bigger and bigger and bigger, and some of its gases will get near this other star that's going around it.
So it feels like a blue star. Would it be like a supernova or something?
Well, there's a way to get a supernova, but we're going to talk about that tomorrow. Tomorrow we talk about how big stars die, and that's where you get supernovas, and that's a little bit different. But yeah, you can have a situation where stuff gets pulled into another type of star that we're going to talk about tomorrow, called a neutron star. And this will cause supernovas. So we'll talk about that tomorrow. But so this white dwarf star, this ball of carbon in space, is a very interesting object. It's like a giant diamond in space, about the size of the Earth, which once was at the center of a star like our sun. And this is how a star builds new elements. So there's also, it's not just carbon. There's also some elements around it that are a little bit lighter than carbon. Do y'all remember the periodic table?
Yes.
It goes helium, hydrogen, helium, and what's the element after helium? Lithium, boron.
Beryllium.
Is beryllium one of them?
Oh, right.
And then nitrogen.
Mm-mm.
Nitrogen's heavier.
Nitrogen's heavier.
Yeah.
Carbon 6. What's 5? Is beryllium 5?
Hydrogen, helium,
It's on the
lithium,
periodic
radium,
table.
boron.
Boron, yeah, okay. Hydrogen, helium, lithium, beryllium, boron. These things can form, these lighter elements than carbon can form in the center of a sun-sized star. But once we get to these bigger stars that are heavier, they've got enough gravity to fuse carbon. And so the carbon starts fusing and the atoms come together to form even larger elements like nitrogen and oxygen and so forth. And so a big heavy star has more layers and has more elements. And these big heavy stars are what are eventually going to blow up and go supernova and release all those elements into space, which can come back together and form new solar systems and form planets like Earth. So all these elements that we have on Earth, oxygen, nitrogen, silicon, called the carbon that you're made of, comes from the center of stars. That's where they're made. The carbon that makes up your skin was once at the center of a star.
I'm sorry
We're all star stuff. That was one of Carl Sagan's famous lines. He's my favorite scientist, and he said, "We are all star stuff. We were everything we're made of, everything on this planet was once at the center of a star. That's how it forms. This is how all the elements form. That's why this is a very important process. You want to know where things came from, you got to learn astronomy. All the atoms that we're made of came from the center of stars. And that's cool. Don't you think?
Neat blood.
Okay, so you're reading chapter